All right. In the last video, we talked about heat, temperature, and the three different types of sensible heat transfer: conduction, convection, and radiation. I spent a little bit of time talking about conduction, a little bit of time talking about convection, a second talking about radiation. But the only reason why I did that is because practically for almost the rest of this module, we are going to be talking about radiation ad nauseum, which means we're going to be talking about it a lot, a lot, a lot. So do me a favor really quickly and just ask yourself, what comes to mind when I think of radiation? If you're like me, the first time I heard of radiation, I thought, well, not probably, I did think Chernobyl, nuclear bombs, Fukushima, Homer Simpson. But actually, radiation is all around us right now. And you would be surprised about to find out about what objects are emitting radiation. Well, stay tuned and we're going to talk about that. So, first, let's talk about what radiation actually is. Radiation is the transfer of energy in the form of electromagnetic waves. So, what you have is you have a particle of air and a particle of anything, and that particle is wiggling around. Remember, last lesson, the wiggling causes temperature. That's what temperature actually is that wiggling. Well, these particles are made up of protons, neutrons, and electrons. Those things have charge to them. And so what happens is, as this particle is wiggling, it's actually emitting a certain level of electricity, or there is a movement of electricity that is occurring. Now, what actually happens way beyond the scope of this class, but what happens is as electricity moves, that causes a magnetic field. And so you get this wave of electricity and magnetism. Now, again, you're not going to have to worry about that. We're not going to go deep into that, but that is why these are called electromagnetic waves. They're basically pulses of electric and magnetic energy. Now, that's just the technical definition. That's as crazy as we're going to get with the definition. But here's what you need to know about radiation. Unlike conduction, which needs direct contact or an intermediate conductor, and unlike convection, which needs a fluid, radiation needs jack crap. Radiation can travel through anything, or it can travel through nothing. Radiation can travel through various media. This is what we call media. Media is some kind of intermediate object, some kind of in-between object that radiation can travel through. Let me give you an example. Let's say you're at home and you have a Wi-Fi signal coming from another room. Now you're in your room, doors closed, windows shut and everything, and there's no empty space. There's no open air between your room and the Wi-Fi router. However, you still get a signal. The reason why you get a signal is that the electromagnetic radiation carrying that signal can still penetrate, pass through the walls to your receiver. It's the same way that cell phone signals work. So radiation can travel through all kinds of things, and radiation can also travel through empty space, what we call a vacuum. So radiation can travel through a bunch of stuff, or it can travel through nothing. That being said, there are many different types of radiation, and I'll actually talk about what's called the electromagnetic spectrum. But what determines the type of radiation are these three key properties: wavelength, frequency, and energy. However, of these three, the kingpin is wavelength. And in fact, frequency and energy are actually dictated by the wavelength. So let's actually talk about what the wavelength is. So When you have that electron or that particle moving up and down, up and down, up and down, that is causing a wave of electromagnetic radiation. You have a peak, then you have a bottom, then you have another peak. Well, the wavelength, which is denoted using the Greek letter lambda, because us geeks love to use Greek letters. Don't worry, I'm not making you join a fraternity or sorority, I promise. But wavelength is simply the distance between two consecutive peaks. So it's simply the distance between two consecutive peaks. We could use any arbitrary part of the wave, but the peaks are just the best place to do it. And it's also worth mentioning that the peaks themselves can be high or low. That's what's called the amplitude. That is, we're not going to discuss that right now. But let's actually talk a little bit about this length. So do me a favor, think about distances really quickly. What are some of the units that we use to measure distances? I'm pretty sure that you've thought about inches, feet, miles. If you're metric like I am, you may think about kilometers, meters, centimeters, millimeters. Well, here's the bad news. The bad news is that for most radiation, those units are simply too big. We need a smaller unit. Enter what is called the micron, also known as the micrometer. A micrometer is 1/1,000,000th of a meter. So if we take a meter and we chop it up into 1,000,000 individual pieces, each one of those individual pieces, assuming that they all have the same length to them, would be a micrometer. So 1 micrometer is 1/1,000,000th or 10 to the minus 6 meters. So that means that we're moving that decimal place over 1, 2, 3, 4, 5, 6. 10 to the minus 6 meters. So really, really tiny. I mean, we're talking about the width of a strand of hair is measured in micrometers. And it is mini micrometers. It's like 10, 15, 20 micrometers. So it's a lot of micrometers. But we worry about this because everything we need to know about a beam of radiation is dictated by that wavelength. Here's why. So let me draw a wave. Here we go. Let's have a wave. How many peaks do we have? So each peak represents a pulse of energy. We have 1 peak, 2 peaks, 3 peaks. Now let's say I took this same length, but I shortened the wavelength. And so now the wavelength is something like this. It is, so now the wavelength is shorter. Again, forgive my bad drawing. But now the waves are closer together. What do you notice? There are more peaks. This is what is called frequency. The frequency is inversely related to the wavelength. The shorter the wavelength, the more peaks you're going to have. The shorter the wavelength, the higher the frequency. And each one of these peaks represents energy. So the shorter the wavelength, the higher the frequency, and the higher the energy. This is what we call an inverse relationship. Basically, when one thing goes up, the other goes down. So longer wavelength, less frequent, less energy. Longer wavelength, lower frequency, less energy. Shorter wavelengths, higher frequency, and more energy. And the type of electromagnetic radiation is determined by the wavelength. Some wavelengths are really, really, really long. Some wavelengths are really, really, really short. Each of those wavelengths behaves a different way. So, how many of you have ever heard an AM radio station before? If you're like me, I've listened to AM radio stations before. How's the signal like? AM radio stations suck as far as sound quality. Well, the reason why is because they have very long wavelengths. I'm talking hundreds of meters. And as a result, very, very long wavelengths means very, very low frequency, very, very low energy. Hence, you don't get a really good signal. However, if we were to shorten it a little bit, we get into FM radio waves. FM radio waves are a little bit shorter. They have a better frequency, they have a higher frequency, they're more energetic. You get a better signal. Now let's go even shorter. Now you're in television waves. These waves have enough energy that they actually can give you sound and a picture. Now let's get even a little bit shorter into what are called microwaves. And yes, the same kind of microwave that you can use to cook your food. Well, microwaves can actually transmit lots of data in addition to sounds and pictures and stuff like that. And in fact, your Wi-Fi signal is a type of microwave. Your cell signal is a type of microwave. Microwave radiation is radiation that is used for a lot of those things. Now, where does the microwave oven come from? Well, the microwave oven comes from one specific wavelength of microwave radiation that makes water very, very excited. And it gets really excited. As it gets excited, it boils. Now, if you noticed, I just talked about 3 different types of radiation. There was AM radio, FM radio, television, and actually microwaves. So 4 different types. Sorry, I lied. 4 different types. Well, 4 different types of radiation. There are many bit more than that. If we even get shorter, we get into what's called infrared. Even shorter than that is visible light. Even shorter than that is ultraviolet. This introduces you to what's called the electromagnetic spectrum. It is the gamut of the different types of radiation there are. Again, AM radio waves, very, very low energy, very, very hot, or very, very low frequency, very, very long wavelengths. As you get shorter and shorter and shorter, energy becomes more and more and more. Now, AM radio waves pass through us harmlessly, as do FM radio waves, as do most television waves. You start getting concerns when we get into microwaves, you know, the whole 5G conspiracy. And if you're next to a microwave transmitter, they may tell you, like, step away, you know, well, what's happening is the shorter the wavelength, the more energy there is. At some point, the energy can become so great that it knocks off free electrons off of the atoms in your body, and that's called ionization. Now, microwaves, infrared waves, and visible light usually aren't a problem. And by the way, visible light, that's radiation that your eyes are sensitive to. So your eyes absorb it, and then there are these rods and cones in your eyes that actually translate it to a color, and it registers to your brain as a color. And as the wavelength continues to shorten, the overall wave becomes more and more energetic. As I mentioned, AM radio waves, television waves, those pass harmlessly through you. And then you get to visible light. That's the light that that is the radiation that our eyes are sensitive to. And so it registers in our brain as colors. And then once you get below that, you get into what's called ultraviolet. Now, one quick thing about visible light, just to talk about this. Have you ever heard of Roy G. Biv? Red, orange, yellow, green, blue, indigo, violet. Well, what if I told you that the person who taught you that lied to you? It's actually in reverse. In terms of shortest to longest wavelengths, the shortest wavelengths are violet, roughly around 0.4 microns. Meanwhile, the longest waves are red, hence the longer wave after, it's what's called infrared. That is approximately 0.7 micrometers. So I'll erase that now, but and then as you get shorter than that, you get to ultraviolet waves. If you remember from module 0 or from module 1, we talked briefly about ultraviolet waves. Those are those really high energy beams of radiation that cause sunburns and skin cancers. Well, as you get even shorter than that, you get into X-rays. X-rays penetrate your skin, get absorbed by your bones, and then emit back outwards, and then get read by an X-ray reader. And that actually helps you see your bone structure. That's what dentists use to see your teeth, or what a doctor will use to see your bones. Getting even shorter than that, you get into what are called gamma rays. Those can knock free electrons off of the cells in your body, creating mutations and causing DNA to break down. And so AM radio waves are harmless. However, as you get higher and higher and higher, as you get shorter and shorter and shorter in the wavelength and higher in the energy, the radiation can become more and more and more dangerous. Can become more and more and more dangerous.